All right, pre-algebra students, today we are moving into our new lesson about classifying real numbers. So our learning target today states that we can describe a number by its specific classifications or types. So in this lesson overview, we know we are going to talk about the differences between rational and irrational numbers and what those numbers even are. We're going to talk about what classifications of numbers are, and then we are going to practice classifying real numbers together. Again, I recommend that you are following along in your guided notes, or you may take notes on separate paper if you choose. Let's get started. So, rational and irrational numbers. They are opposites of each other. Rational numbers are numbers that can be written as fractions or ratios. Think of the word rational, and you see the word ratio in that word. Rational numbers are numbers that can be written as fractions, or they can be written as decimals. Rational numbers include terminating and repeating decimals. And in our last lesson, we talked about how terminating decimals end at a certain point. Like, for example, the decimal 1.5 ends at the 10th place 5. And rational numbers also include repeating decimals. And to quickly remind you of what that looks like, let's say, for example, we have 0.85 repeating. There will be a repetan bar over the sequence that repeats. So this is really 0.85, 85, 85, on and forever. Rational numbers also include the square roots of perfect squares. And in our last lesson, we talked about perfect squares, how those are whole numbers or integers that multiply. You can multiply them by itself. So for example, the integer 2. 2 squared is 4. So the square root of 4 is a rational number. We could also say the same thing for the square root of 100. The square root of 100 is 10, and of course you can write 10 as a fraction or a decimal. Now let's talk about irrational numbers. Irrational numbers cannot be written in fraction form. You cannot write them as fractions. They include non-terminating, and non-repeating decimals. So decimals that go on forever and ever and ever and don't ever repeat. So for example, 1.356148, I don't know. And let's say that pattern is not repeating. We're just carrying that on forever, infinitely many digits. That is an irrational number. And irrational numbers also include the square roots of non-perfect squares. Here's an example. The square root of 2. If you plug in the square root of 2 into a calculator, you're going to get this really long decimal. It starts with 1.4, and then there are infinitely many digits behind those. So non-perfect squares are also examples of irrational numbers. So let's practice. We are going to fill out this table and determine if each value is rational, or irrational, and provide an explanation. Let's start with the first one. Negative 12. Is it rational or irrational? Well, it can be written as a fraction, so I'm going to say it is rational. You can write the number negative 12 as a fraction over 1. So can be written as a fraction. And it looks something like this. Negative 12 over 1. We could also call that negative 24 over 2. That reduces to negative 12. But either way, we can write that as a fraction. It is a terminating decimal, if you will. Now let's talk about pi. If you know anything about pi, it starts with 3.1415, and the digits go on forever and ever and ever. And there's no repeating sequence. So this is one of our most famous irrational numbers. Pi is always irrational. And that is because it is non-terminating. And I'm going to abbreviate here. Non-terminating and non-repeating. Now the decimal 0.6. The decimal 0.6 is a terminating decimal, and we know from our previous lesson that we can write this as a fraction. This can be written as, if you reduce it, 3/5. You would start by writing 6/10 and then reduce to 3/5. So this is a rational number. So we can either say can be written as a fraction, or we can just say that it's a terminating decimal. That's all we really need. Terminating decimal. And the last one I'm going to practice with you is 7/8. This one's a little obvious. This is already written as a fraction, so we can call it rational. 7/8 can also be written as a decimal. So 7/8 obviously can be written as a fraction. So what I would like you to do is I would like you to fill in the rest of the table in your guided notes, finishing out telling whether each number is rational or irrational, providing an explanation, and then there's problems 1 through 6 on the next page for you to practice. Now let's go into classifications. So what even are classifications? Let's just bring up a real-world example. Let's talk about the cardinal. I've got a picture on the screen here. So biologists classify animals, such as cardinals, based on their shared characteristics, from the most general terms to the most specific. For example, the cardinal, if we classify it, is an animal, and it's also a vertebrate, which means it has a spine. It's also a bird, and the specific type of bird it is a passerine. It's a special nest-building bird. So again, from animals to the most specific. And this diagram is showing that passerines are type of birds, birds are types of vertebrates, and vertebrates are types of animals. So the categories kind of nest within each other. And you're going to see the same pattern with numbers in just a second here. So let's talk about these classifications of numbers. We've already talked about rational and irrational, but let's start from the most specific to the most general. So let me label this here. This is specific. Natural numbers are a very unique, specific type of number. Rational and irrational numbers are both very general types of numbers. So natural numbers, these are kind of like your counting numbers. This is how you started counting. This is the set of all positive counting numbers, numbers on a number line, starting with 1. Now let's provide some examples here, and I'll bring up some unique examples. So we've got the number 42. That is a natural number. What about 50 over 2? Well, that reduces to 25, so 50 over 2 is a natural number. And let's say we have the number 100, or 800. So these are 3 specific examples of natural numbers. Now, even more general, including natural numbers, are whole numbers. the set of all positive counting numbers starting with 0. So the only difference between natural numbers and whole numbers is that whole numbers also include 0. Natural numbers do not. So some examples of whole numbers. How about the positive square root of 100? That's 10. 0, of course, is a whole number. And what about 4 plus the positive square root of 4? Well, that would be 4 plus 2, and that would be 6. 6 is a whole number. Moving even more general, we have integers. Integers include the set of whole numbers and their opposite. Usually in math class, we call these our number line numbers. So this is all of the whole numbers and their opposite. So this includes negative numbers that aren't decimals or improper fractions. So let's say we have negative 15 over 3. This would reduce to negative 5. 25 is an integer. Integers can be positive. And what about the negative square root of 81? Well, the negative square root of 81 would be negative 9. Negative 9 is also an integer. Now let's review rational and irrational numbers quickly here. Rational numbers are numbers that can be written as fractions. They include terminating decimals, repeating decimals, and square roots of perfect squares. Just some examples of these include mixed numbers like 12 and 5/7. Negative 6.8 can be written as a fraction. It's also a terminating decimal, and the number 5. And you'll notice 5 can also be called an integer, a whole number, and a natural number. So we're still including all of those other classifications in our examples here. And last but not least, we have irrational numbers. Irrational numbers are numbers that cannot be written as fractions, like we previously stated. And they include non-terminating decimals, non-repeating decimals, and square roots of non-perfect squares. So we could say, well, we know our famous example of irrational numbers would be pi. So 3 pi is irrational. Any number multiplied by pi would be irrational. The square root of 10. We know that 10 is not a perfect square. No integer multiplied by itself equals 10. So that's a non-perfect square. That's irrational. And of course, we have our non-terminating, non-repeating decimals. Let's say, for example, 6.72345 ... Something like that, where it does not repeat, does not terminate. So let's put this into a diagram. Let's create a diagram with all of our types of numbers. And after that, we're going to fill in some examples. So let's start. We see that the biggest box that contains all the other boxes is our real numbers. All of the numbers we're talking about in this lesson are real. Next, we have to separate between rational, and irrational. Remember, rational numbers and irrational numbers are opposites. They do not include each other. They are separate. Both of them are real numbers, though. Let's go into the rational box and let's move further in, getting more specific. Next in the order would be integers. All of the whole numbers and their opposites are number line numbers. More specific than integers would be whole numbers. And lastly, natural numbers are our most specific type of number. So you'll notice that natural numbers can be whole numbers, but whole numbers aren't necessarily natural numbers. The most specific example I can come up with here is 0. 0 is a whole number, but it is not a natural number. So let me cross that off our list. How about the 2 times the square root of 64? If we simplify that, well, we know the square root of 64 is 8. So 2 times 8 is 16. Again, this is 8. So 2 times the square root of 64 is 16. 16 can be a whole number or a natural number. I am going to put it in the most specific box. Okay, so that's been eliminated here. Let's talk about negative 15. The most specific type of number negative 15 can be is an integer. It is included in the set of whole numbers and their opposites. This isn't a decimal, it's just a negative, it's the opposite of a whole number. 16 over 4. If we reduce this fraction, 16 divided by 4 is just 4. 16 over 4 is a natural number, a counting number. It's also a whole number, an integer, a rational number, and a real number. The square root of 75. Now, off the top of my head, I cannot think of an integer when multiplied by itself that equals 75. 75 is a non-perfect square, and we know that non-perfect squares are irrational numbers. That means they are not rational. And negative 12.2. Negative 12.2 is a terminating decimal. The most specific type of number that can be is a rational number. Negative 12.2 cannot be an integer, a whole number, or a natural number. It must be just a rational number and a real number. Let's practice a couple more. So for each of the values, we are going to list all of the number sets to which it belongs. Then we're going to circle the most specific set of real numbers it belongs to. So let's start with A. Let's start with 12 pi. Now we said previously that any number multiplied by pi is irrational. It's going to be a non-repeating and non-terminating decimal. So I can call this a real number. All of these are real numbers. And I can call it irrational. And the most specific type of number 12 pi can be is irrational. Now, what about the square root of 30? 30 is a non-perfect square, so this has to be an irrational number as well. We also know that it's a real number. So this is real and irrational. The most specific type of number the square root of 30 can be is irrational. And C, 45 divided by 5, or 45 fifths. If we reduce this number, it's just 9, positive 9. And we know that 9 is a real number. It is a rational number. It can be written as a fraction. It's an integer. It's in the set of whole numbers and their opposites. And it's a whole number. And actually, one more. This is also a counting number. This is a natural number as well. So the most specific type of number 45 fifths can be is a natural number. You can practice letters D through I for problems similar to these ones. And that was our lesson. Thank you so much for watching. If you haven't already, please make sure you try out some of the additional practice problems. You can check your answers with my filled-in notes by going to the content library of our class notebook and then going to Module 1 Notes. And please ask for support in the Math Help Desk if you need it. Thanks again for watching.